Hi everyone. Now we discuss about one question from GATE 2020, question number 30. So the major product formed in the following synthesis sequence is, so first this is our substrate. First we reaction with organolithium compound followed by THF 78 degrees centigrade, and next step is the potassium hydride which is 25 degrees centigrade THF, and we are using 18 crown 6, that is crown third. So let's see our substrate. Okay, so in our substrate also 1 2 3 4 4 center is there, right? This is alpha beta unsaturated compound, and here is the isolated double bond. So our lithium, so where will we attack? Will attack whether this 2 center or 4 center, I mean, that is we have to find, and followed by the conjugative reaction. So there is a fourth option. In one option, this particular bond, this methyl and this CH2 in the same side, but in this option, this methyl group and CH2 in defined side. This methyl group and CH2 in defined side, and in another case, this methyl group and CH2 in same side. And in one option, there is the ring is get aromaticity, and the fourth option, all other things are basically break. Here to find the correct answer. So the reaction is basically one name reaction, that is the Oxy-Cobb rearrangement, in which there will be the one OH group there will be there, and at the high temperature. So what will happen at the high temperature? There will be a possibility of 3,3 sigma trophic rearrangement. So the reaction will go to the chair-like transition state, and this OH group should be in the equatorial position because due to the eliminate syn 1,3-diacetyl interaction, because other substituent is not there. So after 3,3 sigma trophic rearrangement, we get this product like this, and this is conjugated enol. Okay, so in and all means conjugated double bond and OH. That's why it will tautomerize to corresponding ketone, because the ketone form is more stabilized form. So we'll get this product. But there is another thing is that if we somehow generate the carbon anion in this particular reaction using potassium hydride and 18 crown 6, so that time the reaction will be much more faster, and we can perform that reaction at room temperature, even in low temperature 0 degrees centigrade, and the reaction time will be also less because this carbon anion will stabilize the transition state. That's why this type of reaction will go faster. And the 18 crowd is basically used to tap the potassium ion here. And that's why the reaction will be much more faster than the corresponding. If we use the potassium hydride, that time also reaction will be faster. But additionally, if we add the 18 crown 6, that time the reaction will be much more faster than this type of first example. Okay. So let's come to our question. So this is a alpha beta unsaturated ketone. So this is keto and this is alpha group here, this is beta group here, and the organolithium is in hard in this is the hard electrophile. Okay, this is the hard electrophile. That's why the hard interaction will be good. That's why this reaction will happen whether it's in this position or this position, that we have to find out. So for that, this is our hard center. So this is our soft center. We all know that hard interaction is good and soft interaction is good. That's why our this thing, this nucleophile Li plus and this minus is in soft in nature. That's why our nucleophile will attack at this position, because our nucleophile is hard in nature. Our nucleophile is hard in nature, that's why we'll attack this side, and we will get the product like this. Because let's say we are assuming that this particular group is upside, so due to the steric, the nucleophile will come from the lower side, so that's why the oil group will go upside, and this our particular nucleophile go in the downside. That's why we are getting the particular stereochemistry. So again, this Oxy-Cobb rearrangement will happen. So the carbon ion will be corresponding form, and the potassium will tap by the crown ether. and we'll get the product. So this is our thing. So we can redraw this like this in the chair-like transition state. Okay, in the chair-like form, and this is our chair-like transition state. Okay, so what will happen? We have numbering again: 1, 2, 3. This is 1, 2, 3. So there will be a 3 sigmatropic rearrangement, right? This one will come here, this will go here, this will go here, right? So this is our transition state, and this transition state is the thing is that this is a trans-recurring system take transition state. That's why only one particular type of form is possible. Two type form is not possible if we know the trans-recurring system. And after that we'll get the product like this, and that will tautomerize here again the corresponding keto form, and so the methyl group and this CH2 group in the same side. That's why we get the product like this. Okay, so the stereochemistry is basically decided by this particular bond. See, this is the particular bond, and this bond and this methyl group. See, these two are in the same side. That's why we are getting the product. This CH2, basically this CH2 and this methyl group are in the same side. That's why we'll get the C stereochemistry here. Okay, so our product will be option A, not option C, because that is not possible. And similar reason here, that there is no question of aromaticity, because there is you're getting the more double bond, that is not possible. And this type of ring fragmentation is also not possible. That's why our right option is A. So for this type of video, you can watch this NPTEL video. Thank you.